So, yeah, let's get started. Pulling up on defense by Joshua, we have now Matthew. They've joined the program at basically the same time. They didn't join the group at the same time because Matt has started with working in astrophysics and then turned out that his advisor decided to get up and go to a different place for whatever reason. And Matt was sort of left to fend for himself. So I'm very happy that he decided to actually join my group. And pretty much since that time it was kind of competition between Matt and Josh, who does better. So Josh beat Matt by what is it? It's a couple of weeks, right? But other than that, I think it's kind of more or less a draw. I mean, both have done bang up job, and I really enjoyed working with both of you guys. One thing that I like to point out about both Josh and especially Matt is I think they've done a tremendous job actually serving as mentors to a number of undergraduates. And I think this is really the first time where graduate students have really in my career have really done such a good job doing that, nurturing the interest, the talent who are the next generation. Matt has worked on kind of melding, a few things that part of that came from his background, differential geometry, tensors, and some of the things that I started doing, which was essentially data-driven modeling. And he kind of took those two things together and from something that was fairly ad hoc when he came in, really hooked up, an approach which is really fairly general and physically grounded, which is not sort of data-driven thing, but really melds very nicely the basic physics as well as some data-driven aspects into a very powerful and general model discovery tool. And that's what Matt's going to talk about. So I'll give the floor to him. And thank you.
Thank you very much, Roman. So today I'll be talking about our model discovery algorithm and how we learn continuum models from data. And in fact, just last week, we had a publication in Science Advances, which captures a lot of what I'll be talking about today. So if you like what you hear, I invite you to go read that paper and take what you can from it. So first, I have to acknowledge the people that have really influenced this project. A huge amount of work has gone in from, of course, Roman, my collaborator, Daniel Gurevich, and my predecessor, Patrick Reinbold. They really laid the foundation for a lot of this work. And then I've been very happy to work with talented undergraduates. So Jason Marfie graduated maybe 2 years ago, a year and a half or so. Daiwei graduated last year, and Carlos is still actively working with the group. There are many more undergrads working, but these three have made substantial contributions, and I really wanted to highlight their efforts. So I want to start by talking about a driving factor or a driving force of our work, which is emergence. There are certain systems which display new collective behaviors when many individual objects interact with one another. For instance, on the right here, I have an aerial video of some sheep in New Zealand. And you can see them undergo collective motion to fit through a tiny gate. They're being herded there. And below, there's a collection of starlings which are flying together to form a mesmerizing, almost continuous blob that changes shape in the sky. And reductionism isn't much help here, where reductionism is the concept of taking complex systems and breaking them down into the simpler interacting parts. Studying an individual bird isn't particularly helpful in understanding how this flocking behavior happens. More is different. As you add more things, you get different emergent phenomenon, and computing mathematical models of them from first principles, starting with things like Newton's laws or Maxwell's equations, and arriving at mathematical models is completely infeasible. There's nowhere really to go from there. So the niche that we are trying to fill is finding models for systems which do not have obvious first principles starting points. So traditionally, if one is interested in physical models, you have a base set of predictions and you construct a mathematical model that is consistent with those or you have a set of observations. You make a model consistent with those observations and you iterate that model as more predictions are made. You might push to more extreme parameter regimes and add in new physical effects as they appear. But as the availability of experimental data has exploded, there's been a conceptual change to go directly from observations and physical constraints to the models and remove humans as the bottleneck of the modeling procedure. So today we'll be talking about a specific algorithm that we have spent time developing, which goes from physical data to these models, and it is SPIDER. SPIDER stands for the Sparse Physics-Informed Discovery of Empirical Relations, and it turns gridded data into sparse models that are consistent with physics as we know them in a very general way. So physics knowledge greatly constrains model space. You need models which don't obviously contradict physics. And there are three very general considerations that make this true. Locality, we expect interactions to be local. And so therefore we should get partial differential equations which describe our data because partial derivatives are local operators. We expect that the equations we get should not depend on the particular reference frame or the particular direction we're facing. There should be rotational symmetry. And this tells us that our equations have to transform nicely under such rotations. So we should expect tensor relations. And lastly, we have generally translational symmetry in space for spatially extended systems, space and time. And so any coefficients that were to appear in the model have to just be constants. They can't be fields. Generally, this is applied to experimental data or highly noisy numerics. And we use the weak formulation of differential equations to increase robustness to this noise. Evaluating partial derivatives on noisy data amplifies that noise. It is oftentimes a nightmare. And then we lastly introduce homogeneous sparse regression, which avoids model bias. We make no assumptions about what actually goes into the models we're looking for, which unfortunately means you might not like what you get at the end of the day. But it prevents us from introducing unphysical effects and making unnecessary assumptions. So the general idea of SPIDER can be represented with this flowchart here. And there's a lot of moving pieces. I'd like to go through the experimental system I have spent most of my time at Georgia Tech working on, which is active pneumatics, and use that as a demonstration of this algorithm going through bit by bit, so you get an idea of what's happening. So the experimental system is an active pneumatic suspension made of microtubules. Microtubules are these green rods here, and they form part of the cytoskeleton of eukaryotic cells. Here's an animation that I thought was rather cute from The Inner Life of the Cell. It shows a kinesin motor protein transporting something, I'm not quite sure what, around in the cell by latching onto it and then walking along the microtubules. What's interesting about the experimental setup is that the kinesin motor proteins instead latch not from the microtubule onto something else, but onto another microtubule. And if these are oriented in opposite directions, they introduce a shearing force. If they're pointed the same direction instead of shearing, they just cross-link and make large bundles, which leads to a really beautiful experimental image. Oh, there we go. So here is the video of the experiment. You can see that there is a low Reynolds number flow resembling turbulence. It features a chaotic dancing of topological defects. The size of this image is roughly 0.5 millimeter from left to right. Or if you want to think about it in terms of human hairs, about 2.5 human hairs would fit across this. So these strands here are orders of magnitude smaller than sort of the smallest fibers that we deal with. Also, each frame, there is a second of real time between each frame. This is drastically sped up. These are enormously slow flows on the order of microns per second. And for this reason, this is a non-inertial flow. This is a balance between driving and viscous forces that likely describes this. And this flow is proliferated with topological defects. These are nice features that I feel I should talk about because they're kind of interesting. There are two kinds of them. There are these single bend defects, which are +1/2. These are comet-like defects, and they're self-propelling. You'll see them zip along through the movie. And there are -1/2 defects, which are triangular, and they're not self-propelling. They're simply infected by the surrounding fluid. And you can check. These are quite common in living systems. If you check your fingerprints, I personally have one of each defect on the tip of each of my fingers, which is kind of interesting. So for this system, if we want to apply SPIDER, the first place we have to start with is what data is available to us. So there are three fields you might immediately jump to extracting. The first is the director field, which is a vector field that points parallel to the fibers at every point in space. So here I've taken a +1/2 defect. We've computed the director field with coherence enhanced diffusion filtering. We've plotted it, and immediately there's an interesting characterization that there's a discontinuity line. This discontinuity doesn't have to be here. You can move it to anywhere you want, but the point is that there's a topological problem. N, the vector field itself, cannot globally describe the orientation field. And the way this is remedied is by introducing the nematic symmetry, which maps a vector field to its negative. And if you have this map and you plot both the director field and its negative, you see there's no problem at all. It's really the axis that N points along that's important, not its direction. Its magnitude is also physically meaningless. It's just the axis that it points along. And again, this is the definition. When I say nematic, I'm explicitly referring to this property of the vector field. You could also get a flow velocity. So particle image velocimetry can be used in the experimental images to produce a flow field everywhere in space. Underneath, I've plotted a scalar function, which I think helps show that the flow field has no real small scale structure, at least if you do a little bit of averaging in time. The flow has features that are roughly the same size as the experimental image itself. And it's rather dynamic. As the defects move around, the flow field correspondingly changes. They have similar timescales that they change on. And the last experimental field that you might be interested in is microtubule density. This is something we spent a good deal of effort on, where you take the image intensity, you apply some filter to get rid of the liquid crystal structure so that it's just heavily blurred, and you do some nonlinear fit of image intensity to try to back out a microtubule density. I would specifically like to acknowledge the efforts of Daiwei Sun, the undergraduate who worked with us. Unfortunately, there were a number of difficulties that we were unable to surmount, such as this not being a rigorous measurement of the density. A priori, there's some unknown nonlinear function, density of intensity. We assume that it's monotonic, but ultimately we don't know what the dependency is. The density is discontinuous at defects, which poses some trouble to actually extracting it well. And no meaningful variation in the numerical density was obtained away from defects. In these regions away from the dark defects, the density fields that we were able to obtain are essentially uniform. There's no meaningful gradients. And lastly, it wasn't conserved. If you looked at the continuity equation in time, there was spontaneous creation and destruction of density, which is obviously unphysical. So given these difficulties in extracting this field, we work moving forward assuming that the density is a constant. And specifically, we will only train our model in data that is in this saturated density regime. We are not going to use data from topological defects to arrive at any equations. I must acknowledge existing models. People have put a lot of work into coming up with differential equations to describe the system so far. Usually it's a variant of the Erickson-Leslie equation where you have a director field N, and all of these terms are interpretable. They have physical meaning behind them. The first two correspond to advection by the underlying fluid. The next one is co-rotation, so that if you have any vorticity, your director field will co-rotate with it. And you also have flow alignment. Flow alignment comes from I guess the opposite counterpart of vorticity, the extensile part. And it's different for different kinds of pneumatics. If you have an elongated pneumatic versus a disc-like pneumatic that is squished and has the opposite aspect ratio, you will get different values in this parameter up front. And the last term is the relaxation of free energy, where an initially bent pneumatic will slowly want to rectify and become straight through some thermodynamic mechanism. F, this thing that's relaxing, is the Frank free energy. There are three different ways to penalize gradients in the pneumatic field. And what I would like to call to attention is that already in this model, we have 5 different parameters. And this means that this model can be tuned via careful selection of these parameters to describe a wide range of different liquid crystals, hence its heavy use in the literature. It does a good job for some values for some passive liquid crystal systems. However, 2 of these terms involve gradients of the pneumatic field. And as we pointed out, if we store N on a computer, it's tricky to compute derivatives in these positions where you have effective discontinuities. And so people tend to prefer the Q tensor as a representation of the pneumatic field. The Q tensor is a matrix that is symmetric and traceless. You obtain it by taking the outer product of N with itself, subtracting 1/2 the identity. And N can be recovered as an eigenvector of Q. So there's no information loss. It's explicitly pneumatic. Here is a picture of QXX for the +1/2 defect we were looking at earlier, and you can see it's continuous everywhere, except there's discontinuities in the derivatives at the defect location right here, but otherwise it's fairly well behaved. It's a nice field. And you could do the exact same dynamics as the Leslie-Erickson equation, but now in terms of this Baris-Edwards equation. So here, this is the first case where we see the same physical phenomenon being described by different representations of mathematics. It is not the case that every phenomenon has a single description. There can be redundancies, and it's not even clear which one is the fundamental representation of such a physical law. Again, this is explicitly nematic. It bakes in this fact that the vector field has no inherent direction, and it's much better suited for numerical simulations, certainly for the numerical simulations we did in terms of this tensor, and is again locally equivalent to the Leslie-Erickson law. For the flow, the incompressible Navier-Stokes is generally invoked. So we have mass conservation via the incompressibility condition, and we have the Navier-Stokes equation, where the first term represents inertial effects, the flow is advected inertially, and the right represents internal stresses. We have the divergence of a matrix here that represents the deformation forces on a small cube or square of matter. And for this particular regime, I mentioned the flow speeds were enormously small. And so we are justified in assuming that the left-hand side vanishes for this particular case. And really the dominant terms are going to be some balance of stresses on the right-hand side. So all of this to say that many different stress tensors can exist, and people have considered many different ones in the literature. There are viscous stresses, active stresses, bending stresses, Ericsson stresses. You can look at Marchetti and Reiskin for a nice review of some of those stresses. And the viscous stress has three contributions, one of which is the classical isotropic stress of Navier-Stokes. The other two are phenomenological Leslie stresses, representing coupling between the liquid crystal structure and gradients in the flow, and sigma alpha being the canonical active stress used in many active pneumatic descriptions. Again, there's another 4 parameters that people can typically tune to try to reach agreement with the theory, or agreement with experiment. But the real problem is that when we think about the experiment that we have a bottom plate, some water, the microtubules are trapped between a water-oil interface, and a top plate where the velocity is effectively vanishing on the top and bottom because of no slip condition. And we expect a fundamentally 3-dimensional flow, with the microtubules only experiencing a 2-dimensional cross-section of it. We only have 2D flow data, and therefore a 3-dimensional model isn't of much use to us. We can't actually evaluate derivatives in the Z direction. We don't have access to that information. So we need a 2-dimensional effective model where we only consider gradients in X and Y and also in time. And a big problem is that all first principles models are expected to be valid in the 3D case, but they shed little light on the effective 2D models. Because there's a natural rest frame of this system, right? It's trapped between stationary plates. There's possible Galilean symmetry breaking that might manifest. You can have phenomenological terms like Rayleigh friction that enter as new forms of drag. You can have non-trivial parameter drift from an unknown Z dependence of the flow. If you average in the Z direction, coefficients that were once equal to 1 may drift and now be 0.93 or something like that. So beyond all the coefficients I've previously shown, there's a whole new zoo of them, which results in 2D effective theories possibly having dozens of system-specific parameters, the vast majority of which have not been measured. And so we're left with a conundrum of not really being able to compare experiment and theory rigorously. You can choose certain parameter values and do numerical simulations and show that different aspects of the theory are matched, but it's really difficult to rigorously test different choices. So now that we've discussed the data and possible descriptions of it, what derivatives exist, we're going to have to talk about symmetries and how symmetries enter into this problem. They are, I would say, one of the key parts of this problem into simplifying the possible classes of models via irreducible representations. So I'd like to take some time to talk about tensors. Tensors transform linearly under symmetries. For the purposes of this talk, we are going to think of a matrix as a rank 2 tensor. It is a linear map from a vector to a vector. Typically, people write it in this notation in most intro physics classes. And when you do a summation, when you act with a matrix on a vector, you're effectively summing with an index. So you can write this in index notation on the right, where one index of the matrix is being summed with an index of the vector field. And for the rest of this talk, we are going to drop the summation symbol. We'll abide by the Einstein summation convention, where the presence of two identical indices implies a summation over those two indices. Now, there's nothing special about an object with two indices. We could also create an object with three indices. This is a rank 3 tensor, and any summation with a vector there could then give us a matrix. You could imagine acting on this vector to get a rank 2 object now where the k's have an implicit summation and disappear, where the i's and j's are still free and get passed on to the result tensor. And you can use this procedure to inductively define rank 4, rank 5, and higher tensors. You can have an arbitrary indexed object, and that arbitrary indexed object can be contracted with other tensors. So examples of these in physics, for rank 0 tensors, unindexed objects, those are just scalars. Things like pressure, temperature, density, things that don't have any kind of directional information to them. Rank 1 tensors are vectors. They correspond to velocities, electric fields, director fields, somewhat. Rank 2 tensors, we talked about the stress tensor entering into fluid dynamics. It's a good example of that. Rank 3, we have the cross product defined by the Levi-Civita symbol. In rank 4, the most common one I know of is the Riemann curvature tensor, describing transport on curved surfaces. These things are very important for mathematical modeling, and they can enter in any way that tensors are allowed to interact. And in tensors, in this particular context, transform in a very particular way under rotation. Typically, if you want to rotate a vector, you just create a rotation matrix and you act on that vector to get your new vector. However, in index notation, you just contract one of the indices of your rotation matrix with one of the indices of your vector. And for rank 2 tensors, each free index needs a rotation matrix, which is contracted with it. We can abuse matrix notation somewhat to write one of these as a transpose, and then use the fact that the transpose of a rotation is its inverse to show that this is a similarity transformation. It's just a change of basis via rotation that most people are familiar with. And you can imagine, generalizing this to rank 3 and higher, where each index of the rank 3 object accumulates a rotation operator. But for rank 3 and higher, there is no useful matrix representation. And so if you want to write really general physical laws, this will not cut it. It won't be enough. I would like to point to birdtracks.eu, the graphical notation of Predrag and Penrose as an alternative if you want to draw diagrams instead of these indices. And I would say that they both serve very valuable purposes. Some proofs are clearer in one versus the other. So it's sort of dealer's choice which one you use. But for this talk, we'll use index notation. And the 3 tensor operations, which relate tensors of various ranks, are the tensor product, which take 2 vectors. So in this case, I've taken 2 vectors. I've multiplied them next to each other without contracting the indices to produce an effective rank 2 tensor. You can do things like index permutation. Rearranging the indices does not change how the tensor transforms, so it's still a tensor. And you can do contractions, which is the most important thing on this slide. Contractions are when given a tensor, you pick 2 indices to sum over and it reduces the rank by 2. So for this case, for a rank 2 tensor, there's a unique contraction you can do, which is the trace. For a rank 3 tensor, there are actually 3 different choices you could make, depending on which index you want to remain free. It could be the first, second, or third. And all of these resultant vectors, which just have the single free index I, will generally be different for an arbitrary rank 3 tensor. So it's important to be able to compute all of these things and consider their impact on physical models. So the framework I want us to have, the picture in our mind, is that physics exists in every tensor representation. You can have scalar laws of rank 0. You can have vector laws of rank 1, tensor laws of rank 2, even higher tensor laws of rank 3. And we shouldn't make assumptions about where the physics lives. It might have representation. So in the case of the Ericsson-Leslie equation, it had a rank 1 representation and a rank 2 representation. But it's possible that there is no rank 1 or rank 0 representation, and you will only see this physics if you look in the rank 2 space or higher, as is the case with general relativity. The Einstein field equations are manifestly rank 2. Irreducible representations are then, once we've understood that physics can exist in any of these tensor representations, we can recognize that these tensor representations themselves can be further broken down. For instance, if I take a 2x2 matrix, 1, 2, 3, 4, and I rotate it by 70 degrees. I apply that rotation matrix to the left and to the right. I get a substantially different one on the right. The elements have changed rather drastically, some more drastically than others. But if I consider the trace, if I add the diagonal elements on the left, I have 1 plus 4, which is 5. And if I add the diagonal elements here, I get 5.25 minus 0.25, which is also 5. The trace transforms independently. In fact, it doesn't transform at all. The trace will be the same no matter what rotation you apply to it. And so it contains independent information from the general matrix. Specifically for objects of 2 indices under the group of rotations, there are 3 irreducible representations that you can split any general physical equation into. You can compute its trace, you can subtract the transpose to compute the antisymmetric contribution, and you can add the transpose to get the symmetric contribution, but then you also have to subtract the trace to get the symmetric trace-free moment. These all require no information about each other in order to rotate. And in fact, in 2 dimensions, both the trace and the antisymmetric part don't transform at all. Both of them are completely invariant to continuous rotation. Again, constructing irreducible representations is an important part, but not a main point of this talk. Bertracks EU again delves into how to construct irreducible representations of any symmetry group you have in your R. And also the Q tensor, Qij, that we motivated to describe the nematic crystal order. This is actually part of the symmetric trace-free space. There is no projection into the other 2. It lives solely in this symmetric trace-free space, which is part of the reason we subtracted the trace in the first place. The trace is not physically meaningful, and so we can remove it and keep it as a minimally transforming object. So instead of physics existing in every tensor representation, we think of physics existing in every irreducible representation across different tensor representations. So the rank 2 space now splits into the rank 2 trace, the rank 2 antisymmetric space, and the rank 2 symmetric trace-free space. In particular, the rank 2 trace space is just scalars times an identity. It's very boring. None of the physics that we will discover in this space could not be identified in the rank 0 space, and so there's no reason to ever investigate it. So up to rank 2 under rotations, there are 4 independent spaces that physics will generally live in. Now, fortunately for us, we actually have more symmetry than just rotations and reflections. I didn't specifically talk about reflections, but it's the same irreducible representations in this case. We also have this nematic symmetry, this fact that we can flip the direction of n, and that further splits all of our representations again into even and odd powers of n. Because even powers of n, when the sign of n changes, even powers of n will stay the same. For an odd power of n, changing the sign makes the overall product change sign. And so the irreducible tensors of this problem are traceless symmetrized tensors via the rotation group, and then exclusively even and odd powers. And then general physical relations will be linear summations of nonlinear terms inside these representations. So the representations tell you how a general nonlinear term transforms, but then once you construct some set of them for a particular representation, any linear combination could in principle describe a law of physics. And again, translational invariance, which I invoked in the beginning, implies constant coefficients. So there are 4 representations in the rotation space, and there are 2 in the nematic space. So up to rank 2, there are 8 in total, and we've considered 6 of them explicitly. It's not that these 2 are not physically motivated. Physics also lives there. It's just we found everything we needed by looking at the first 6, and I didn't feel like writing code for the latter 2. In particular, so there are certain equations we expect to live in certain places. I guess I should point that out. The mass conservation equation should be nematic invariant. It shouldn't care about the sign of n, and it should be a scalar. The nematodynamics in the form of the Erickson-Leslie equation should be a nematic covariant, it's odd powers of n, vector. The Barris-Edwards equation describing the dynamics of Q should be in the symmetric trace-free nematic invariant space. We have expectations about what physics is there, but again, that just motivates us to look there. We make no assumptions about what physics is there defined by the data. So once you understand which irreducible representations of your symmetry that physical law lives in, you have to then actually construct libraries of terms which could possibly enter into equations. And then once you have these, you can use what I'll show with the weak formulation to create coefficient equations, which can be solved for the laws of physics. Libraries are used to model empirical relations, these physical laws. This is exactly from the last slide. We have some set of nonlinear relations with coefficients. And again, libraries are collections of equivalently transforming objects, all living inside the same irreducible representation. I'd like to point out that libraries are formally infinite. There is no official stopping point for any library. You can construct scalars of arbitrarily high polynomial order, but because we don't have an infinite amount of time, we have to make some decision about where to cut off the library generation process. Physical considerations enter here, and also complexity considerations, but in this case, physical considerations actually turn out to be rather powerful. So we've talked about how slow the velocity field is in this case, so we're only going to keep terms linear in the flow velocity. We'll assume that any nonlinearity is too small to actually impact the dynamics. Although we did augment the field with quadratic terms later and showed that it had no effect. The data is exceptionally smooth and well resolved, and so we're only going to keep derivatives up to second order. We're not going to look at anything third or higher. And lastly, the magnitude of n, the director field, we set it to 1 because the magnitude is not a physically meaningful field. And so there's no limit to the number of times it could appear in any nonlinear term. It doesn't change the magnitude of that term. And so with these considerations, there is a finite cutoff that contains terms that match these assumptions. And the libraries can be constructed systematically. There is no ambiguity about what terms you can fit with these assumptions. So to show you an example, when I first introduced the Navier-Stokes equation, I talked about all the different stress tensors that could appear. And I showed a scary slide with about 6 or 7 different stress tensors. Those are not the only stress tensors that could enter the problem, not even close. For instance, if you allow, I'm gonna skip this slide for now. If you allow all possible stress tensors consistent with our assumptions, there are actually 26 of them. Although the literature only considers 7 because those are the ones that you would kind of expect from first principles. So we are allowing things which are typically not even thought of as possible for entering equations to be identified in a data-driven fashion. So this is the largest library that we constructed, and it's the only one I'll show you today. It's a total of 60 terms, and this could model all possible linear relationships between the flow and the nematic order. Some linear combination of all 60 of these tensors has to describe leading order dynamics. And in fact, across all of our libraries, we have a basis of 126 tensors, and this forms a systematic basis for all physics. We don't know what the physical interpretation of that physics would be, but we know to leading order, this is it up to rank 2. So anything we find, we can then study and learn the interpretability of, but this is a completely general space to look for physics in. I also wanted to point out that 126 is large, but feasible. So the strong form of partial differential equations is when you add up these nonlinear terms. So these F's are any of these terms, right? So the F could just be the flow velocity. The F could be the time derivative of the flow velocity. It could be anything here. Some sum of them vanishes everywhere. That's the strong form of partial differential equation. And the problem is that our data is noisy, right? And so it is unlikely that any relation, even if it is very approximately true, it is unlikely that this right-hand side will vanish. There will be noise that contributes to it. And so instead, we're going to be considering the weak form of partial differential equations. So instead of evaluating it point-wise, we pick space-time domains, omega. We pick chunks of space and time, and we integrate each library term over that numerically, given our data that's been gridded. And we also have a new degree of freedom, which is this weight function phi. We can choose it to, in principle, be anything we'd like. And this gives us a great deal of flexibility in the algorithm. I will describe many such use cases for it. But the point is that this is an easier set of equations to enforce, because now you're allowing the noise to average and you're allowing things to actually converge towards 0, even in very noisy data. I will say that there is a 3-dimensional fluid data set for which we can discover accurate physical relations with up to 300% noise, which I think is pretty remarkable. Even to eyeball, you can't see anything for that particular data set. Weight functions we typically use are weight functions, which are polynomial envelopes which vanish at the boundaries. So here are a few different choices. You can raise the power of this weight function to make it more narrow or more broad, depending on what you'd like. But in general, choosing larger subdomains is better because it allows more averaging. You can also introduce in spatial variation. You could add in a Fourier mode so that you're actually sampling spatial variation of your the temporal or spatial variation of your fields. It's really up to you. So the power of the weak formulation comes from a few different principles. The first, hopefully people who've taken Calculus 2 will recognize integration by parts. Let's say for some nonlinear function, I need to integrate my weight function times the x derivative of u. What's great about the weak formulation is that as long as the envelope function that I chose vanishes in the boundary, I can just rewrite it like this. I can move the derivative from my noisy experimental data onto the analytic weight function. And I can take this derivative exactly. I no longer have to finite difference my data for this particular term. This gives a great deal of flexibility and is useful, especially because terms of that form appear all the time in physics, specifically in transport equations, where fluxes are describing the dynamics of some quantity. We can also use the weak formulation to remove unobserved latent variables like pressure. If you can't observe certain variables, clever choices of weight functions can effectively remove them from your dynamics so that you can still discover the underlying dynamics, even without those measurements. And for our case, we use the weak formulation to additionally mask discontinuities, like topological defects. And it constructs a natural coefficient equation. Here we have a sum C alpha. I've just rewritten the weak form of the differential equation. And this is effectively a matrix times a coefficient vector equaling 0, where this coefficient equation is written here and is a normalization term that is discussed in the thesis, but we'll gloss over here. So one component comes from which subdomain you're integrating over, and the other component refers to which library term you're actually looking at. And so you end up with constructing this matrix G by sampling some tensor field, multiplying it by a weight function. So you have these products here, and then through numerical integration, you get a single number that then goes into a matrix. Overall, our data set is about 9 million measurements if you multiply out the pixels. And each of these boxes takes about 30,000 measurements, averages them to produce a single number. And you can imagine filling up this matrix by computing different integrals corresponding to different weight functions or different subdomains. And in total, implementing all 6 irreducible representations, I like to count. It was 1,600 lines of MATLAB. Okay, so the final part, you have this coefficient equation that you've constructed from your irreducible representations. How do you get a human interpretable model out of it? We do this with sparse regression, in our case, homogeneous sparse regression. So we have our matrix where each column corresponds to a nonlinear tensor. We're trying to approximately solve G times C equals 0. And the analytic solution for this is obtained by taking the singular value decomposition, right? You can minimize the norm of the right-hand side by looking at the right singular vector associated with the smallest singular value. And then what you can do is you can remove terms iteratively. You could say set term number 4 to 0 and recompute the SVD and see if it actually meaningfully impacts the residual on the right-hand side. And what you'll find is that for these huge libraries, many terms don't impact the residual at all. They have no statistical influence on it. And so you can remove insignificant terms, or sometimes you can add significant terms back if you've irrationally thrown one out, or not irrationally, but irresponsibly thrown one out early on. To arrive, this iterative procedure removes terms in a greedy fashion to either raise the error the least or lower the error the most, and eventually will converge to a sparse model, a finite number of coefficients with a finite number of nonlinear terms that very well approximates 0, just as well as the full library would. If I had 60 columns here, it would have a comparable residual to just these 3. And in that way, you can know that those other effects aren't particularly physically important for the system. And it's possible for multiple equations. There can be multiple solutions to GC equals 0. And so once you find one, you can simply discard the largest dominant term and start again, repeat, and look for subsequent equations, find multiple equations in the same libraries. Okay, so we looked at all of these, and across the 6 libraries, we found 9 equations here. I've grouped them by irreducible representation. So these 2 came from the nematic invariant scalar library and so on. And what's interesting is that these are, there is redundancy between them. While we found an equation in each irreducible representation we looked in, they are not all independent of each other. In fact, if I color code them by physical meaning, here you can see there are in fact 3 classes of equations that we found. We found mass conservation. We found 5 equations in green, which effectively describe the fluid flow. And then we found 3 equations in red. And hopefully you'll somewhat recognize this first one is the Erickson-Leslie equation. We found it directly from the data, making no assumptions. And we found the Barris-Edwards equation as well, the second last one describing the dynamics of Q. And we found a third representation in the antisymmetric space, which turns out to be the time derivative of the angle as well. And these are all equivalent. You can change between them, whichever one is your favorite for use. So the most compact form of the model are these 3 equations here. We have mass conservation, which we kind of expected going in, although it's not trivial. This is 2-dimensional mass conservation. We expected the 3-dimensional divergence to vanish, and we found that, in fact, the 2-dimensional divergence very well approximately vanishes away from defects. We found the Erickson-Leslie equation, but without a right-hand side. You might remember that when I introduced it, there was a relaxation of free energy, and we did not see that when we did our reconstruction in any of the representations that we found. We found 3 of them, and relaxation of free energy was found in none of those representations. And the last equation was rather bizarre, and this is what I meant when I said you might not like what you found. This last equation, in its most simple form, doesn't appear to be a stress balance. Rather, it's a kinematic condition. It is a constant extension rate. It is a dot product of the pneumatic tensor with the flow gradient that is effectively a constant over the entire field. And what's even more interesting is by plotting these after we've discovered them, we can tell which ones need to be generalized to describe the entire system, including topological defects, because we didn't use topological defects to identify these. The mass conservation equation and constant extension equation do need some modification. However, the flow alignment equation seems to be well behaved over the entire domain, even arbitrarily close to defects. So to show you that these hold in strong form and not just weak form, here you can look at the finite difference time derivative of n, and here you can look at the equivalent one reconstructed from our discovered partial differential equation. And you should see excellent agreement, at least I see excellent agreement between these 2 slides. Although the left is a bit noisier because again, we're finite differencing in time and I haven't applied much smoothing to this at all. And you can see even in these black regions, these black lines are isolines of intensity denoting where topological defects are present. Even near topological defects, there's good agreement between both sides. Here is the constant extension rate equation, although it is multiplied by the Q tensor because this is the original formulation we found it in. And you can see that the left-hand side and right-hand side have excellent qualitative agreement. Although there's more fluctuations on the right-hand side, they're still very, very similar. But there are problems near topological defects if you look carefully. So our data-driven results are that there was no rotational viscosity or elasticity identified. We measured the flow alignment parameter lambda to be 1, and there was no length scale found in our model. All of these are very interesting, and in fact, all 3 of these were corroborated by an independent concurrent analysis out of Tufts and Brandeis. And so we know that we're not making things up totally from this. But the rather interesting result is that the flow does not seem to be described by an effective 2-dimensional stress picture. A canonical equation used in the literature is the balance of isotropic stress with active stress, and the experimentally observable extension rate, which is experimentally observable through our identification of equations, instead appears to determine the flow. Okay, I have a few predictive slides, which I think we have time for. So do these equations work? Yes, we can numerically integrate the flow field forward in time. On the left, we have the director field from experiment, and on the right, we have the simulated director field where we are solving the Erickson-Leslie equation without any elasticity, or at least the minimal amount of numerically stable elasticity. And we get, I think, about 94% correlation after about 4 correlation times. So we're able to very well predict the future given the boundary conditions and initial conditions of experiment. Also, this constant extension rate, it is very difficult to solve near defects because of the features of the equation, but it allows us to make predictions and compare the flow fields of confined topological defects. So if you take the stress picture that is canonically used, I'm going to reference Luca Giomi's work, where he shows that a +1/2 topological defect will have 2 counter-rotating vortices, which lead to its self-propelled motion. And our constant extension equations, when properly regularized and solved on a numerical grid, produce the same qualitative flow field. All this to say that the observation that there are 2 vortices around a +1/2 defect is not unique to a particular physical theory. Multiple physical descriptions can provide the same qualitative flow fields for these defects. Although I will say there is some rather substantial disagreement for the -1/2 defect case. But I think that there's a lot of influence from the numerical grid and some symmetry breaking going on in this case. But it still has the 6-fold symmetry that one would expect. There have been many successful applications of Spider, many papers on theoretical scalings and choices of weight functions, as well as 2 applications to experiment. Patrick Reinbold had an excellent application to thin film turbulence, and you can also check out our paper again that just came out last week. For future work, we're interested in learning fluid dynamics from pure kinetic simulations, using this to learn the emergent phenomenon of just ordinary Newton's laws, as well as more active systems like the Weizsäck model and classical flocking. And then I would like to thank all of my friends and family who have supported me over the years. I wouldn't have been able to do it without you. And yeah, you've made Atlanta a second home. I'm really happy that I ended up here and spent time here. So in summary, Spider allows knowledge synthesis directly from data, focuses on the discovery of interpretable mathematical models. Physical constraints are essential for making the problem tractable. This approach this is perhaps the biggest thing I want to stress. It's systematic modular in general. If you don't like how we do sparse regression, you're free to change that out, but our library generation has no ambiguity. And this can be applied to many spatially extended systems. Especially, it's applicable to disciplines outside of physics. If you have a spatially extended system and want to understand its dynamics, this is a viable path to it. And I will leave up the 2 GitHub links. There's one for a MATLAB implementation, and then the second one is Daniel's Python implementation.